Hello, this is Patterns of Inductive Reasoning, Section 1-1 of the Prentice Hall Geometry Series. We are starting out with just a little bit of vocab. Inductive reasoning is reasoning based on patterns. So you're looking for a pattern and trying to determine if it's multiplication, division. It doesn't just have to be numerical math though, it can be other patterns out in the real world, and we're going to do a couple examples in a moment. Conjecture is another vocab word. It is a conclusion reached using inductive reasoning. So we're forming a conclusion based on the patterns that we are seeing. The third vocab word is counterexample, and a counterexample is one example that shows that a conjecture is incorrect. A million examples do not prove something, but it only takes one example to show that something is false. So those are our three new vocab words for this section. We're going to show a couple examples with patterns. Patterns can be figured up with numbers, shapes, words, etc. So we've got a couple patterns here to look at. The first thing we want to do is determine what the pattern is. In this case, we want to determine, is it addition, is it multiplication, subtraction, division? In this case, if we add 3 to 3, we get 6. But if we add 3 to 6, we do not get 12. So we're adding 3, we're adding 6, we're adding 12. It's kind of hard to describe that pattern, but another way of looking at it is each time we are multiplying by 2. So if we multiply 3 by 2, we get 6. 6 multiplied by 2 is 12, and so on. If we wanted to continue that pattern, we simply would do 24 times 2, and we would get 48. To find the next term, we do 48 times 2, and we would get 96. So that is the process for continuing a pattern, is first to determine what the pattern is, and then to go on and continue it. This pattern next happens to be visual. We call this line that goes across a diameter, and currently in the first circle there's 1 diameter, the second circle is 2 diameters, and the third circle is 3 diameters. So if we wanted to continue, our fourth circle in the pattern would have 1, 2, 3, 4 diameters, and our fifth circle would have 5 diameters. So we have 1, 2, 3, 4, 5. Okay, could have done a little bit better about getting that in the center, but it gets the point across. So 4 diameters and 5 diameters. The next thing we're going to look at is inductive reasoning. We have a couple an example of inductive reasoning. We have a pattern here: 1 plus 3, 1 plus 3 plus 5, 1 plus 3 plus 5 plus 7. What we're doing is the sum of the first so many odd numbers. Sum being addition, and of course odd numbers every other starting with 1. In the first sum, since we just have 1, the sum is 1. In the second pattern, 1 plus 3 is 4. The third pattern, we get 9. In the fourth pattern, we get 16. Upon further investigation of those numbers, we find that 1 is actually 1 squared. We're making a connection here. 4 is actually 2 squared. 9 is 3 squared, and 16 is 4 squared. What you'll want to notice, and sometimes you have to look for a minute to find that pattern, but 1 is the number of terms we're adding. 2 is the number of terms we're adding here. 4 is the number of terms we're adding here. So if we take 4 squared, we do get the sum of 16. To make a conjecture, we're using this pattern, and we want to finish the statement. The sum of the first 30 odd numbers is, well, if this is the sum of the first 2, and this is the sum of the first 4, then we want to think further and say, okay, the sum of the first 30 would have to be 30 squared. So the sum of the first 30 odd numbers is 30 squared, or 30 squared is 900. So that is our conjecture. Moving on to counterexamples. Counterexample, again, proves a statement is false using one example. So we have the square of any number is greater than the original number. When we look at that statement, that includes all possibilities. And remember, we only have to find one that proves it false. So that one could be 1 squared is not greater than 1. So that's the one statement we need to prove it false. Next example, you can connect any 3 points and make a triangle. Well, when you connect them this way, that is true, you're making a triangle. But our counterexample could be when all 3 points are linear. If those 3 points are linear, then they certainly don't make a triangle. So this would be our counterexample. We have a couple additional examples to consider. Finding a pattern and continuing with the next 2 terms. Again, we seem to be going down, so it's either subtraction or possibly division. It doesn't appear to be going down by the same amount, but it does appear to be going down by half. So we're either multiplying by 1/2, you could do division by 2 as well. So we're taking half each time. So if we take half of 48, we end up with 24. And if we take half of 24, we end up with 12. So these would be our next 2 terms. A couple more examples. We find a counterexample for each conjecture. A number is always greater than its reciprocal. Remember, reciprocals are the fraction of the number flipped upside down. So for instance, the reciprocal of 2/3 is 3/2. That's an example of reciprocals. So if we consider 1, the reciprocal of 1 is 1/1, and 1 is not greater than 1/1. They are actually equal. If we consider 1/2, our reciprocal of 1/2 is 2/1, which is just 2. And 1/2 is definitely not greater than 2. So there's actually 2 counterexamples. And we could find more if we wanted. For part B, if a number is divisible by 5, then it's divisible by 10. Well, you could actually use 5. 5 is divisible by itself, but 5 is not divisible by 10. So 5 is a counterexample. In fact, any number ending in 5, for instance, 15, 25, 35, those are all counterexamples. So this concludes section 1.1.